Okay, let's start. So we were discussing about geometric corrections in the last lecture, last session, and then we could not discuss radiometric corrections due to the time constraint. So let's quickly do a couple of problems on radiometric correction, and then we'll move to digital image processing. So yeah, so first of all, as we know that radiometric errors, they arise due to errors in the sensor itself. So if one or several of the detectors in the sensor, they stop working or they go out of calibration, in that case the radiometric error arises. So radiometric errors are of different types, like um, random bad pixels, or line start or stop problems, line or column dropouts, partial line or column dropouts, or other errors which were mentioned in the lecture. So when we look at an image like this, um, first we will try to identify what type of radiometric error is there. So looking at this image, can you tell me what type of radiometric error this would be? Okay, so it will be it's random bad pixels, because these pixels A, B, C, they are scattered randomly in this image. So to correct for this error, we will go for the simplest possible method, which is averaging its neighboring pixels. So to find the value of A, we would need to average all these pixels. Which is equivalent to, it's some 109.12. So we will round it off to 109. Similarly, we can take averages of these pixels and these pixels to find B and C. So you can verify this. I calculated this, and B is approximately, so it's 131.75. So we'll round it off to 132, and the value of C is 86.87. So it's 87. So we'll move on to the next problem. Yeah, so the second one is an example of line dropout error. So this type of error, they are either corrected by replacing the erroneous line with one of its neighboring lines, or we can take average of the line preceding and succeeding it. So this is the formula which is used to correct for these line dropout errors. So basically it's just average of these two values. So this is 7900.
Will you please repeat it?
163. Yeah, which one?
In that column you have written some values. Where did you get?
Yeah, so this is average of the line which is preceding and succeeding the dropout line.
Okay.
Okay, so the average is taken so that the line doesn't look too artificial. It looks natural because the neighboring pixels would have similar values. So we take average of the two. Okay. Okay, so let's start with digital image enhancement. So why do we need digital image enhancement? So remote sensing images which are captured, so they always might not be the best images suitable for analysis. So there might be so the visual appearance of these remote sensing images might not be very good. So we apply image enhancement techniques to make the visual appearance of these images even better. So uh, yeah, so due to poor brightness and contrast, these remote sensing images lack better appearance. So we apply image enhancement techniques. So a transform function is used to map. Uh, so this is an input image. So a transform function is used to uh, change the input raw image into the output image. So this transformation, it can be used for contrast enhancement or contrast adjustment, contrast stretching, and so on. Yeah, so mathematically we can write it as g of x comma y is equal to t of f of x comma y. So this is the output function, this is the transformation function, and this is the input function. Right. So this was explained in the lectures also, that this transformation it can be uh, it can be uh, global, local, or point. Right. So when this transformation is applied on all the pixels of the image, so in that case, it's called a global transformation. In case if it's applied on only a few pixels, then it's local transformation, and if it's applied only on one pixel, then it's called a point transformation. So point transformation. Okay. Uh, so point transform, it can be categorized into three parts. First we have linear point transform. Yeah, so this point transform can be categorized into these three different types of operations, which we will see one by one. So examples of some linear point transform are identity function or inverse function, and for non-linear point transform we can have square function, square root function, or logarithmic function, or exponential function, power function, and so on. So yeah, so in point transform, so all of these different types, so they are functions which will be applied on each pixel. So on each pixel, if this is the value, this transform function will be applied to get the output image. Okay. So let's see an example of linear point transform, which is this. So here, so let's look at this image. So this first image, this is appearing very dark to us. So this is the histogram of this first image. Here the values are, this is 0 to 50. So this is an 8-bit image, right? So the available range of DN numbers in this image will be 0 to 255, and out of this available range, only values between 0 to 50 are used in this figure. So because it's on the lower side, we see that this image is appearing very dark, right? So 0 to 50, and this is, yeah, this is the histogram of this input image. Now to make it visually even better, to uh, enhance its appearance, we will apply this linear point transform on this figure. So this is the function which is the transformation function. So this is y equals to 5x. So for every value, every DN number in the input figure, the output, the DN number in the output figure will be 5 times as that of the input. So if this is my histogram in the input figure, this, so the range of this histogram is 0 to 50, and here when we enhance it 5 times, then on the y-axis the range becomes 0 to 250, and then corresponding to every point on the x-axis. So here, let's say if this is 10, so corresponding to this 10, we will have a 50 over here. So we plot the frequency of this histogram on the y-axis over here. So in this case now the range of this figure was between 0 to 50, and now here it becomes 0 to 250, and we see that now this image is taking up a higher range of DN values. So because of that, the I mean the quality of this image, I mean the visual appearance of this image has uh, increased. I mean it has become better. So this is the application of linear point transform. So there, so we apply different such functions depending on the application that we are looking for or the aspect of the image that we wish to enhance. So depending on that, we will be using different types of transformation functions. Is this slide clear to everyone?
Yes.
Okay. So this is an example of inversion, which is another type of linear point transform. So here, remember we saw identity, we saw inverse. So inverse is another type of linear point transform. So here the function is given as g of x comma y. So in case of inverse operation, what happens is the brightest pixel becomes darker and the darkest pixel becomes the brighter. So during photography and all, you must have seen the negatives of the images, which looks like this. So in that, this inverse operation takes place. So here L minus 1, L is the total number of gray levels available in that image. So for an 8-bit image, our L will be 256, and for others so on. So for an 8-bit image, this function will be g of x comma y is equal to 255 minus f of x comma y. So the inversion function will look like this with the slope of -1. Okay. So we'll solve a problem related to inversion. So obtain the digital negative of the following 3x3 grayscale image. So this is an 8-bit image. So based on this information, can you please try to solve this? Let me know when you're done, then I'll solve and you can check if it's matching with your answer. Also, this is the reference that I am using. So this is a digital image processing. This is the book by S. Reader, and I am following this for examples. You can find various numericals in this book, and you can also practice. So let's solve this. Uh, so in an 8-bit image, we have 256 gray levels. So yeah, as we just saw, g of xy will be 255 minus f of xy. So this so for pixel 1, we have so and so on. So pixel 3 is 55. I hope you all got the same answers. Okay, let's move ahead. This is fine, right?
Yes, ma'am.
Okay, so we'll move on to nonlinear point transform. So here we saw that these many functions can be applied in nonlinear point transform. So yeah, so let's look at their formulas. For square function, right here what we need inversion square root. Uh, this is 7 because this is a 3-bit image and total number of gray levels are 8. So this is 8 minus 1 for square root function. For logarithmic function, so yeah, these are all the functions, all the non-linear transform functions. So based on this information, you can attempt to solve this question. So assuming that the gray level is 0 to 7, uh, so total number of dn values is 8. Apply the following transformation. So we need to apply inversion, square root, square function, logarithmic function, and power function, and these coefficients are given over here. So you can try solving it for this image for some time, and then I'll solve along with you. So I think you should write to NPTEL support team for this. So as a TA, I'm not sure about the exam process. So you can write to NPTEL support. Okay, so let's solve this. So for inverse function, this will be is equal to 7 minus f of x comma y. For a square function, this is f of x comma y square. So the values here will be 1, 4, 9.
Excuse me. In that inverse function, that first number you have written 8.
Yeah. So I'll explain that. Okay. Uh, yeah, 7. Sorry. Yeah, sorry. 6. This is 6 5. 6 5 4 3. 4 9. So in this image, we see that all these values 9, 16, 25, 36, 49. So all these values, they're more than 7, right? And the range that we have is only up to 0 to 7. Right. So all of these values which are above 7 will be stored as 7 only. So this image will look like this. 1, 4, 7, 7. Again 7, 7, 7, 7. And 4, 9. Right. So here all of these pixels, they have the same value only. So this image will appear very bright after this transformation. So it will kind of saturate the image. So this transformation will not enhance its appearance, but instead it will make it look more saturated. So we have to see that how our image appearance would look after applying each transformation. So we have to pick a suitable transformation method to apply on the image based on our requirement. So yeah, after applying square function, we will get a saturate. I mean, for this image, it will look like this. So for, let's see how it will be for the square root. So I have calculated this from before. You can verify this. So here, uh, when we round off these values, it will be so after the square root transformation, we will get an image which looks like this. Then next is logarithm. So here we have been given values of a as 0.5 and c as 1. So we have g of xy is equal to 0.5 into log of f of x comma y plus 1 plus 1. So here this plus 1 is added because if fxy has value 0, then log of 0 is not defined. 7 minus f of x comma y. So that is the inversion function. So in inversion, what we said is that the darker pixel becomes the brightest, right? So we so 0 has to become 7, 1 will become 6, 2 will become 5, and so on. So when we mathematically write this, it will be L minus f of x comma y, and L here is sorry, L minus 1. L is total number of brightness levels available. So here it will be 8 minus 1. So this is 7 minus f of x comma y. So this is the inversion function. So this function you apply on each pixel to get an inverted image. So here try substituting the value. So if we substitute fxy is equal to 0, we will get 7. If it's 1, we'll get 6, and so on. So our darker pixel would become the brightest, and the brighter pixel would become the darkest. So that is the inversion function. Okay, I hope that was clear. Okay. Yeah. So for logarithmic function, we apply this formula, right? So suppose let's calculate it for 1 pixel. So if we are calculating it for 1, then it will be 0.5 into log of 1 plus 1. So log of 2 plus 1. So log of 2 is okay, 0.3. I'm getting 1.15. Okay, can you please try? So similarly, you can. Okay, A and C is given in the question itself here. So it can be anything. I mean, A and C, it can be any constants. So depending on the values of A and C, your log function will change. So based on your function, your transformation, I mean your image transformation will appear different. So you can actually play with the numbers and try to generate different kinds of images, and then you can understand how different values of A and C change the values. So you can try this logarithmic function. And next is power function. So it is c into f of x comma y to the power r. C is 1 and r is 1.2.
In square root, will you show that matrix, please? Previous slide. Here also, after rounding up, around 50% values are 6.
Yeah. So a lot of values over here, there are 6. So this image will also appear bright, but not as bright as the square function.
Okay.
Yes, if we get values greater than 7, then it will be stored as 7 only, because this image is 8-bit image only, so it can store values only up to 7. Sorry, it's a 3-bit image, sorry. Okay, so this is the power function. So this will be 1, 2. So here after rounding off, this 1 will stay 1, this will be 2, this is 4. So now this 8.58 will round off to 9, but 9 can only be stored as 7. So this will also be 7, 7. 3 and 4. So you can change the values of this power and the constant. So here it was c is equal to 1 only. So you can change these values and try to see how the image will change. So these were all the non-linear point transforms. So now so non-linear point transforms are clear, right?
Yes.
Okay. So now we move on to piecewise linear transform. So let's go back to our previous figure. So yeah, we did linear point transform. We did non-linear point transform. Now let's do piecewise linear transform. Okay. So in so piecewise linear transform. This is also used to manipulate contrast of the image. So here, selective pieces of histogram, they are linearly contrast stretched. So before what we saw is in linear transform. So here and all. So everything uh, here, in this range, the entire histogram and all the dn values in the range of this image, they were stretched using the same function. So uh, I mean, if one dn value is getting stretched 5 times, all the values will get stretched 5 times. So here in piecewise linear transform, what we do is we split the dn values into different ranges. So r1, r2. So suppose if this is an 8-bit image, then it will be from 0 to 255. So we split it into different parts, and then within each range, the function, the output image will uh, will be mapped differently. So in this image, it will map according to, so between 0 to r1, then this is r1 to r2, and r2 to 255. So in these three ranges, we have three different functions. So let's do a numerical on piecewise linear transform. So what will be the dynamic range of an image if the slopes of the image are given as L is equal to 0.2, M is equal to 0.5 and N is equal to 1. Assuming the image to be 3-bit, 3-bit means 2 to the power 3. So we have value 0 to 7 with R1 is equal to 2 and R2 is equal to 5. So you can maybe note down these, or I'll write the equations here. So okay, so maybe you can try to solve these equations. So this nu and w, v and w, so this will be the value corresponding to this function at r1, and w will be value corresponding to this second equation at r2. So I have made this plot, so you can try to find the range on y-axis. I mean the output range of this figure when these linear transforms are applied. Okay, so let's solve. So for the first line, the equation would be 0.2 into r. So between 0 to 2. So for values 0, 1, 2, they will follow this equation. So for r is equal to 0, r value would be 0 itself. For r is equal to 1, it will be 0.2, 0.4. So this is here. This value would be 0.4. So this is your v. Are you getting it? I mean, are you getting the same answers? Okay, so
You got that value is 0.4 against r equal to 2.
yeah.
Against yes, r equal to 2. And you have
Hello.
written here in the graph.
Hello.
Huh.
Madam. In the given problem, value of r is not given, but you have considered r equal to 0.
No. So R it ranges from 0 to 7.
Okay. So we have to consider r equal to 0.
So here,
If r is not given. If r is not given.
this is here. So we are trying to calculate how the output will look for all the input values. So this is 0. You will have 1. This is 2. Then there will be 3, 4. Then here we have 5, 6, 7. So these are all the DN values that the input image can take, because this is the 3-bit image. So, and these are the piecewise linear transform functions that we are applying on the input image based on their ranges. So between 0 to 2, we have this function. Between 2 to 5, we have this function. Between 5 to 7 is this function.
Okay. Thank you.
So for r is equal to 3, now the function will be this. So we have s of x comma y is equal to m is 0.5 in this range. 0.5 into r minus r1. So r minus 2 plus 0.4. So here if we substitute r is equal to 3, we should get, so this is 1.5 plus 0.4. Is it clear? We have 0.5 So corresponding to 3, 4 and 5, we have 0.9, 1.4 and 1.9. So here R2 is at 5. So this will correspond to 1.9. So this W is equal to 1.9. Now we calculate for the third stretch.
Excuse me.
Huh.
That is that equation is m into r minus r1 plus nu, right? So r1 is given, that is 2, and that new value is
So this is V. So this is
c.
this. So we can find the equation of this as so y minus y1 is equal to y2 minus y1 upon x2 minus x1 into x minus x1. So this is the equation of straight line. If 2 points are given, then this is the equation of straight line, no? So this is the same thing that we are doing here.
No, that in place of v you have taken 0.4.
Yes.
Is it that slope or which value exactly you have taken? V stands for
Yeah, see. So in this equation, when my r is equal to r1, so when r is equal to 2, in that case this term will be 0,
yes.
right? So that is the value of y which remains at y is equal to 2, r is equal to 2. So here when I substitute r is equal to 2, in that case my y value will remain 0.4, right?
Yes.
That is this value.
No, no. What I'm saying in that equation, m into r minus r1 plus v. So r1 is 2, it is already given, and m is the slope of that line, that second line. It is
Yes.
0.5,
Yes.
and that v value you have taken 0.4. So
Yeah. So
where you got that value?
yeah, we just calculated this here, this value.
Okay.
So let's just look at this. So here, this is v.
Okay.
V is the output value of this function at r1,
Yes, yes. Okay, I got it.
and then for r2, at r2 it will be w.
Mm. Okay.
Okay. So here the equation of this line would be, now here n is given as 0.1. So we have, okay. Let's add a new slide. So here we have s of x comma y is equal to n is now 0.1 into r minus 5 because r2 is 5 plus w. Now w that we calculated here is 1.9. So it's 1.9. So now when I have r is equal to 6, for r is equal to 6, this is my function. So when I substitute 6, I will get s of x comma y is equal to, so at r is equal to 6, my function value is 2. And for r is equal to 7, it will be 2.1. Right. So my function, which was in the input, its range was 0 to 7. So here, so this input range, sorry, this was 0 to 7, but then at output the pixel corresponding to 7 is 2.1 only. Okay, so this is 2.1 only. So my input range from 0 to 7 in the output image is becoming 0 to 2.1. So can you tell me if after the this piecewise linear transformation, this image would appear brighter or darker? Yes. Right. So from a higher range of DN values, we went to a lower range. So if our previous histogram was something like this, then our new histogram would be like this. So in this case, the transformed image, it would appear darker. So based on these slope values, we can tell if the output image would be brighter than the input image or it would be darker. So if these slope values, they are greater than 1, then the output image would be uh, brighter, and if they are less than 1, then it would be darker. So here, now if suppose my image was spanning only 0 to 5, and then my output, so my slope is greater than 1, and like this in different ranges. So if my slope is greater than 1, so in this case it is spanning a higher range than that of my input image. So in this case I will get a brighter image. Is this clear?
Yes, would you please discuss the advantages and disadvantages of this technique?
So here, yeah, so you have to select the function based on your utility. So if your image is very dark, then in this case, or in piecewise linear transform, if suppose so suppose your histogram, it has different peaks. So in that case, you can use different functions for each range. to enhance the image. So you can use different mappings in different range of DN values.
And any disadvantage of this function?
Disadvantage as such, so yeah, so if you're not careful, then you might end up producing a darker image. I mean, if you do not choose a proper function, like what happened here. So anytime before applying any kind of transformation, it is better to look at the histogram first, look at the distribution of the image, and then based on what feature we want to highlight in that image, we should choose the function in uh, whatever range of DN values we want.
Hello,
Hmm.
madam. I have got one question regarding how to balance the histogram in which
Okay.
input and output matrices are given.
Input and output
Uh,
matrices are given.
and how to choose the grayscale? How
Uh,
to choose how to choose the grayscale?
no, so this will be given. This, I mean, this will be the property of the sensor. So it will be, it will depend on that. So grayscale you cannot choose as it will be the property of the image itself.
No, it can be anything. Can
Uh,
we restrict up to 0 to 7, or can we go for go beyond?
so it will depend on the radiometric resolution of your image. So um, I mean, this you cannot change as such.
Okay, because in the earlier assignment, it is given like that. It is the values are DN values are more than 20.
So this the it depends on the radiometric resolution of your image. So your
Okay.
when you download a satellite image, you
Uh,
have some information about that image. So
uh,
it will depend on from what is the resolution of the sensor. So if the sensor is more sensitive to different brightness values, in that case the sensor will have more more range of DN values. So the sensor will have higher radiometric resolution. So it might be 8-bit or 16-bit or even more. And if the sensor is not very sensitive, in that case it can only sense small range of um, intensities. So in that case, suppose if it's a 3-bit image, then it can only differentiate between the intensities at only it can only differentiate between 8 different intensities. If it is a better sensor, it can differentiate into even higher levels of intensities. So that will depend on what kind of image you are using. So this we are just taking examples of different kind of images. So that's why here we are using a 3-bit image. In previous class we used 8-bit image. So it will be different for every image.
and one more thing, madam, if the 8 by 8 bit data is given,
Hmm.
then how to find the kernels for
Uh, in this example,
no, in the previous,
which example?
in the assignment number 3.
In assignment 3. Oh, okay, I'm not allowed to discuss any of the assignment questions.
Okay, okay, okay.
Okay, sorry. We can discuss it after the assignment deadline is over.
Okay.
Okay, okay. Okay. Okay, so we finished all the three types that we had covered here. So for point transform, yeah, we did linear point transform, yeah, we did non-linear point transform, and we did piecewise linear transform. So
Actually, while discussing different techniques and related problems, you should also discuss the advantages and disadvantages, because now we are facing many assignment questions and the details are not given.
all
So,
right. So from next assignment onwards, I'll try to do that.
okay, okay,
Okay.
thank you.
Yeah. So all these three, they are examples of grayscale mapping. So now we will look at the histogram modeling part of point transform. So uh, so here we apply different types of transformations on the, I mean, on the histogram. So for contrast stretching, so here we see that in this image, so this is an RGB image. So here, this is the it's an 8-bit image. So here, uh, this is the restricted range in which the red pixels are, I mean, the values of red pixels, DN values of red pixels are restricted to this range. Then for green pixels, they are restricted to this range, and for blue pixels, it's a very small range. So out of all the available values, these values are occupying a very small range in this image. So because of that, the contrast in this image is very low. So in order to enhance the contrast of this image, we stretch the histogram to its, uh, I mean, to its full range. So here, the figure on the right side, here we see that the red, green, and blue, all the pixels, they are occupying all the values from 0 to 255. So here, the darkest pixel on the left side, it is it is now corresponding to 0 in the image on right side, and similar operations are have happened for green and blue as well. So here, suppose uh, this A and B, and this is C and D. So this is my original range, and suppose I want to change this range to C and D in order to enhance the image, like how it is done in this image. So it need not be from 0 to 255. I can change this range accordingly based on how I need to amplify the image. So here, this range from A to B, it can be changed to C to D. So first, um, what we do is, uh, first we subtract A from all the values of this histogram. So we have f of x comma y minus A. Then we normalize this by the range of these values, and then multiply it by this range, the desired range. and then add this constant C. So this will be the output. So now this histogram, it will spread over values from C to D. Sorry. So let's do a numerical on this. So this process is called range normalization. So a gray level image is given whose range is 10 to 60, and it is necessary to transform this image to another image B whose range should be 120 to 180. So what should be the gray level transformation? And this is the given image. So if we follow this function, then we have f of x comma y. So here our range is 10 to 60. So this is A to B. So A is 10, B is 60, and then this is 120 to 180. This is C to D. So first we need to do fxy minus 10, then normalize it. Plus 120. So for fxy is equal to 10, this whole part, this whole term will be 0 because the numerator over here will be 0. So here first value will be 120. So our output matrix will have first value as 120. Then for fxy is equal to 15, five by 50. Uh, does someone have a mic on? This is 126. And then other corresponding values are 132 and 168. So after the range normalization, this will be the matrix after this gray level transformation. Is this clear? So yeah, so this is another type of transformation. So in case of thresholding, so there is a particular threshold value above which a function can take a different form and below which the function can take a different form. So suppose this is 1 for f of x comma y less than equal to a threshold, and it's equal to 0 for f of x comma y greater than the threshold. So it will look like a step function. So suppose this is the threshold. So this is 1 and this is 0. 0 to 255 if it's an 8-bit image. So applying this threshold function, it will eliminate all the values after this threshold. So all the values after the threshold will appear dark and all the values below the threshold will appear bright. Or it can be the other way around as well. So it can be like this. So here,
Will you please repeat again regarding brightness? You told something, actually I missed it.
yeah, so in thresholding, so there is a threshold value below which, so for every pixel, the function, it will check whether the value of this pixel is above or below the threshold, and then accordingly the value for that pixel will be decided. So if that pixel value, if the input value of that pixel is below the threshold and this is our function, then so if we are using this thresholding function, and suppose the threshold value here is 100 and my pixel value is below 100, then it will be transformed to 0. If the pixel value is above 100, then it will be transformed to 1. So let's look at this example on the right side. So look at this image. So the dn values of different elements, they are given on the right side. So this white triangle, it corresponds to 255. This dark square, it corresponds to 0. This is 128. The background here is 162 and this triangle is 192. Okay, so here first we have threshold as less than 100. So in this case, the thresholding function is the first one. So here, for the values which are less than 100, they are appearing as 1, and the ones which are greater than 100, they are 0. So here this t is equal to 100. So look at all the objects in this picture which are below 100 and all the objects which are above 100. So here only this dark square is below 100 and everything else is above 100, right? So in that case, this dark pixel, so uh, all the dark squares, they are appearing white here and everything else is appearing dark. So here this type of thresholding function is applied. Now here if we change the threshold value, if we make t as 150, then for all the values less than 150, they will be 1 and everything else will be 0. So here we see that this and these two objects, they are less than 150. So all the squares and all the circles, they are appearing white and everything else is dark. Now here the threshold is t greater than 200. So all the objects, so now here it's this. So all the objects which have value dn values greater than 200, now they will appear uh, brighter and everything else will be dark. So here these values are so this is 1 and the matrix is 0. So here above 200 we have only one value. So these shapes are above 200, so that's why they are appearing brighter. And similarly for this, everything above 175 will have fxy is equal to 1, and everything below that will be dark, will be 0.
Excuse me.
Does this example make
Suppose
it clear?
first one. T is less than 100. You have written.
Where here?
The first one T is less than 100. So
Hmm.
only square is having value less than 100.
Hmm.
So here only squares will appear
Hmm.
because we have taken T less than 100.
Hmm.
And whatever values are less than that, they will be brighter,
Hmm.
right?
No, less than 100 is brighter,
Hmm.
greater than 100 is darker.
Yes.
Huh.
And again, in case of third one, T is greater than 200. It is given.
Hmm.
Greater than 200, only that pentagon shape is there.
Hmm.
Only pentagon shape is there.
Right.
And in this case, only those two are visible. Rest of the things are darker.
Yes. So here in both these cases, the functions, the thresholding functions are different. So here it is like this. Sorry. So here for these two functions, it's this, and for these two functions, it's this. Is it all right?
Okay. Okay. In second case, that means in first case, the values which are within that range, those will appear brighter.
Hmm.
In that third one, it is given T greater than 200. In that case, the values which are above that range, only they will appear brighter, right?
Hmm. Right. Yeah, so this is thresholding. So in case if you want to remove some low values from an image, so if there are some erroneous values, then you just apply this thresholding, and then you can get rid of all the lower values. All right, so next is histogram equalization. So in case
One more thing,
huh,
the values, the thresholding limit which you have taken T 100 or 200, that you are assuming randomly. Or,
see, this is for the sake of this example.
okay.
Huh. So you can choose any threshold values depending on how your image is, and I mean how are the DN values in your images.
Okay.
So suppose if you have a scene where you have some water bodies, right? So these are water bodies, and everything else is suppose vegetation. So we know that water bodies will be very dark, right? And there are some very small scattered water bodies also. So water body, so this is a suppose it's a near infrared image. So we have seen from class before that in spectral reflectance curve we have seen that water reflects very, I mean it does not reflect in NIR. So in NIR it will appear very dark. So in this image, suppose it's an 8-bit image, your uh, range of your water pixels, it will be very small. So it will, suppose it ranges from 0 to 20. In your 0 to 255 available range, suppose your water pixels are ranging from 0 to 50, 0 to 20, and rest all is vegetation pixels, so they have higher values. So suppose they have values greater than 200, right? Now from this image, if you need to extract, I mean if you need to show the water bodies in this case, then you will apply the threshold at 20. So you will say, show me only, I mean, if you want only values before 20. So in this case, your water bodies only, they will appear as bright and everything else will appear dark. So your water bodies will be enhanced in your output image. So you will be able to see it better or extract those features better. Vice versa, if you want to extract the vegetation, if you want to look at the vegetation, then you can apply. So here we said it's above 200. So you can apply a threshold at 200. So in that case, your vegetation will appear bright and your water bodies will appear dark. Is that fine?
Yes.
Okay. So before we saw contrast stretching, there we increase the contrast in our image by changing the range of our histogram. So this was AB and then we kind of changed it to CD. So, but the shape of the histogram, it would remain same. So in histogram equalization, what we try to do is, we try to uh, bring, I mean, we try to change the shape of histogram. So suppose this is the input histogram. We try to make it such that all the intensities, so if this is 0 to 255, histogram equalization is the process in which, so here after the equalization, all the intensities will have approximately similar frequencies. So after the equalization, so this is the histogram of the input image, the first one, and after doing the histogram equalization, it will look like this. So more or less the frequencies of all the dn values, they are more or less similar in this image. So how this process is done is, um, it takes 4 steps basically. So sorry. Find cumulative sum of histogram values, then normalize the values by total number of pixels. Okay, so I'll explain these steps using an example. So here, this is perform histogram equalization for the 8x8 8 level image described below. So here, the available range of RDN values is from 0 to 7, and so if we try to plot the histogram here, so we have 0 to 7, 1, right? So for 0, we have total 8 pixels. Suppose this is 8 pixels. For 1, we have 10. Here we have 10. For 3, we have only 2 pixels. For 4, we have 12 pixels. 5 has 16 pixels. then again 4 and 2. So this is roughly the shape of this histogram. So now we will try to do histogram equalization in this image. So first what we do is we write down all the total number of pixels corresponding to each DN value. So 0, 1, 2. So here we write cumulative sum of the total number of pixels. So here it's 8. Then here we add these two. So this will be 18. Then we have 28, 30. Then we normalize these cumulative values using the total number of pixels. So this is total number of pixels. So we normalize it here. So 8 by 64, 18 by 64. So this is the uh, normalized uh, cumulative values, and then we multiply it by the highest possible DN value. So we will multiply it by 7. So this turns out to be approximately 0.875, 1.968.
What is 7 exactly?
Yeah, so this is an 8-bit image. So the maximum possible value over here is 7.
Okay. Thank you.
And then so we approximate them to closest integer 2. So all the pixels which had DN value 0 previously, now they will be 1. Everything which was 1, it will be 2. Then 2 and 3 will be mapped to 3. Then 4 will be mapped to 5. 5 will be mapped to 6. And then 6 and 7 will be mapped to 7. So after doing this, the histogram, I mean the shape of histogram should be such that um, the entire intensity range, it will have more or less similar values. So here if we say, so one has total 8 pixels. So 0 does not have any number, any pixels. 1 has 8, 2 has 10, then 3 has approximately 12. So this has 12, this has 12. 6 does not have anything, and then 7, it's 6. So I think this should be like this. But so I did not explain this better, I think. Mm. Yeah, 6 has 16 values and then this has 7. Okay, so yeah, this will be the result after the histogram equalization. So we'll try to solve another problem. So this does not explain it very clearly. So let's try to do this problem and see. So here first we will see that how many values each pixel has. Alright, so these many number of pixels are there corresponding to each dn value. Now we'll calculate the cumulative pixels. So this will be 0, 1, 3, 5, 6, and 16. Then we divide everything by 16 and then multiply by 7. So after histogram equalization, these will be the new values of this image. So here so yeah, so 1 becomes 0, 2 becomes 1, 3 is 2, 5 corresponds to 4, 4, 6 corresponds to 6 only. Yeah, so this will be the transformed image.
show that slide again. In previous case, it was given 8 into 8, right? So total number of pixels we have taken 64. 8 into 8, previous
Yeah,
problem.
yeah, yeah. No.
And
Uh, yeah. So yeah, this was 64. Now
it is
here
all,
we have 16 only.
yes, here it is 16. And that's 7,
7 is because it's a 3-bit image. So these
yes.
will give the range from 0 to 7.
So
Hello,
will it
madam.
be given in the question that 3-bit image? It is 3-bit
Uh,
image. Will it be
yeah,
given in the question?
given. It will be given.
Okay.
Madam,
Huh.
I want to ask one question regarding this. That
Hmm.
is histogram equalization.
Hmm.
The value 7 you are considered because the grayscale is up to starting from 0 to 7.
Yes.
If the grays if the grayscales are different
Yes.
other than say 7, say 20, 22, 23
Hmm.
up to say 55,
Hmm.
then what is the multiplying constant in the CDF column?
Yeah. So in that case, so if
In
the
place of
grayscale is
in
higher,
place of in place of 7,
hmm.
what is the value to be taken?
Yeah. So if it's a 4-bit image, then you will have total 16 values. So the
Please
value
explain with respect to 8 by 8.
for 8-bit image.
8 bit image.
Yeah. So for 8-bit image, your values will range from 0 to 255. So in that case, it will be 255, the multiplication factor.
Multiplication factor will be 256.
255.
255. Okay.
Hmm. Yeah. So how you assign the values? Okay. So this is after applying the histogram equalization. So after this whole process, the pixel values are changed. So 0 here we saw that for 0 the value is 0. For 1 it was 0.4375. So because it's less than 0.5, so it will be approximated to 0. So the value of 1, all the pixels which have value 1, they will be changed to 0. Then similarly for the next pixel onwards, the values will be changed.
Okay, got the point.
Okay. Yeah. So until now, what I mean, all the operations that we saw. So there, we were applying all the transformation on one pixel itself, and uh, based on operations on that pixel, the value corresponding to the same pixel in the output, we were getting that. So. Here, suppose this pixel is f of x comma y. So we were doing operations on individual pixels. So this, it was point operation. So on every pixel we do the same operation, and based on this we were getting output which was g of x comma y, and it was based on this transformation function. That is before any calculation. Which value? One second. Which value? These values? Okay. So here I just counted the number of pixels which are corresponding to these DN values over here. So if I have 0, so in this I looked at this matrix. So here there is no 0. So the number of pixels corresponding to 0 is 0. Now for 1, I have 1 single value. So this is 1. For 2, I have 2 twos. For 3, there is 2 threes. And so on. Is that fine? Okay. Now in neighborhood operations, what happens is we okay. In neighborhood operations, for 1 pixel, to find the output value for 1 pixel, we also consider the pixels which are surrounding it. So we will also apply transformations on these pixels in order to calculate the output value for this pixel. So that is neighborhood operations. So yeah, so these neighborhood operations, they are carried out by using different spatial filters. So now we will look at different types of spatial filters and how they operate. So uh, first we have so these spatial filters, they can either create a smoothing effect or a sharpening effect in the input image. So after we apply this filter, your image will either be smoothened or it will appear very sharp. So in this smoothing, we have two different types. So we have averaging linear and in sharpening we have other filters like Laplacian. So we will look at these filters in detail. So in averaging linear, so this is like convolution, and in non-linear we have filters like max, min, or median. So yeah, here it's mean, for example. So yeah, let's look at one example and then we'll see. Yeah, so are you able to see the animation? So this is an example of averaging linear filter. So here what is happening is this kernel, it's moving across the image. So this is 5 cross 5 image, and the kernel size is 3 cross 3. So it will take uh, it will take average of all the 9 pixels. It will move across the image from top to bottom, and then it will take average of all the pixels which are lying in that 3 cross 3 area. So here the output image will only have 3 cross 3 dimensions, because for the edges this filter cannot be applied. So this is an example of averaging linear filter. So this will create a smoothing effect in the image, because the values are becoming more uniform over here. So 137, 126, 132, and then the output is more uniform. I mean, it's 144, 144, 146, and so on. So this is another example of how different sizes of averaging linear filters, they how smoothing they make the image. So this is the original image. This is an image after this is 3 cross 3. This is 5 cross 5, 9 cross 9, 15 cross 15, and 35 cross 35. So after applying each filter, the image is becoming more and more smooth, and it's becoming smaller and smaller. So the bigger the size of the filter, the smaller the image will be, and more will be the smoothening effect. So this is averaging linear filters. So yeah, this is an example. So here, uh, here the filter that we saw, it was uniform, and
Will you explain this slide again? Whatever you told.
which display.
This one. Yes, yes, this one.
Okay, okay. So here, so we saw this, right? You saw this,
Yes,
yeah. So here the size of this filter is 3 cross 3.
yes,
Huh. So for 3 cross 3 filtering, the original image will look like this. Okay. Then as we
yes,
increase the size of the filter, so it will become more and more smoothed, because each output pixel value, it will be an average of all the surrounding values which are there in that box. So this value, suppose, okay, so for 3 cross 3, this value is an average of all these values. Then this value would be an average of all these values. So there will be a lot of averaging. So because of that, the image, it loses the it becomes less sharp. So there is more smoothening effect, because all the pixel values will be in the same range only. So there, the variation which is there in the original image, it will get reduced. So if your original image values corresponding to these pixels, if they were 126, 134, 140, or 120, 144, 136, say. So suppose they were ranging from 120 to 144. So in that case, if you have, it's a 8-bit image from 0 to 255, so this will be a certain range of values, right? 120 to 144. But then after averaging all these values, they are becoming, they are coming closer. So this will, it will be an average of its nearby pixels. So these values would would be, it would be a smaller range. So this is 127, 124. So now here, this is taking up an even smaller range. So here the image will be, it will appear more smooth. So the more and more your size of the filter increases, your image will start appearing more and more smooth, so it will look more blur. Now when we look at the sharpening filters, we'll see how those filters affect the image. So it will be like opposite of this. So there, the contrast, intensity contrast, it will be enhanced, so the image will appear even more sharp. So you can choose these filters based on what kind of application you're looking for.
okay,
Okay, okay. Yeah, so this is an example. Use the following 3 by 3 mask to perform the convolution process on the shaded pixel in the 5 cross 5 image below. So before, the mask that we applied, it was simply taking average of all the pixels. So there was no weighing. In this mask, so before our 3 cross 3 mask, it looked like this. it was equal. All the pixels were getting equal weightage. In this case, this is a weighted mask. So here the central pixel is getting more weightage. So the value of the central pixel would have, I mean, it would control the output value more than its surrounding neighboring pixels. So here the diagonal elements, they are all 0, and then along x and y we have 1 by 6, 1 by 6, 1 by 6. So if we apply this mask on this 5 cross 5 image, so for this the edge pixels we will not be able to calculate. So only we will be able to calculate only for this 3 cross 3 matrix. So if we apply this transformation, so let's calculate for 50 say. So for 50, the 3 cross, so 50 pixel has to be in the center, and then this filter, it will sit on top of it like this. So the value of this pixel would be 30 into 0 plus 40 into 1 by 6. So it will be the pixels of the image into the mask. So 50 into 0 again, 40 into 1 by 6, 50 into 1 by 3 plus 80 into 1 by 6, 35 into 0 plus 255 into 1 by 6 plus 70 into 0. So this value is yeah, this value is around 85. You can also cross check with me. Alright, so the output vector after performing this filtering, the so the central pixels, they have values 85, 65, 61, 89, and then uh, for these edge pixels we do not have a value from the filter. So uh, here only these values from the original image itself, they are filled here.
Will you please tell the values of this middle pixels?
This here,
Yes, the first one is 85, then subsequent values.
what?
Uh, in the middle pixels, you have written the values like 85, the 65. So those are from the given matrix, means you obtained.
So after we apply this transformation, so for this pixel we calculated, right? For 50 we calculated that it was around 85. Then we will do the same kind of transformation for all the other pixels. So for 80, it will be, the filter will move and it will be here.
Okay, okay. By shifting, you calculated and directly you have written the values there.
Yeah, so for the second one, it will be here. Then for 60, it will be this third window. So the filter will move, and accordingly the value of each pixel will be calculated.
Okay.
So I think our time is over. So there were other things to be discussed which I could not cover today. So we will do this in the next session, and then we will also look at principal component analysis, and we'll try to do some numericals on that. Yeah, I will share the video link. And also some of the concepts I could not explain properly today, so I'll try to explain it better in the next session. So thank you all for joining. We'll end the session here.